In this next piece, we want to add on another concept dealing with moles known as molarity. Molarity is a way that we use to quantify the concentration of a solution. So if we're looking for how much of the solute is dissolved in the solution, we're going to use concentration, and there are many different variables for concentration, molarity being the most common one that we are going to use. You can also see variables such as mass percent, something called molality, parts per million, parts per billion. There's many different concentration units, but since we're on the topic of moles, we're going to focus primarily on the term molarity. Now, by definition, molarity is the moles of solute divided by the liters of solution. Solute is the term that we use for the substance that is dissolved in the solution. If you had NaCl aqueous, NaCl is your solute. The solution is that mixture of solute and what's known as the solvent. Our most common solvent that we're going to use is going to be water. So all of our aqueous solutions have the aqueous compound, the compound we've labeled as aqueous, as our solute, dissolved in the solvent of water. The unit that we label it with is a capital M, and every time you see capital M, you need to think moles divided by liters. Moles divided by liters. To find molarity, you're always going to take the number of moles of solute that you know and divide it by the liters of solution. To go in reverse, to go from molarity back to moles, you will take molarity and multiply by liters. Because molarity is moles per liter, if you multiply by liters, you end up with moles. So we're going to look at a number of example problems. I think the easiest way to illustrate this is with examples. So let's start with just basic examples of converting to molarity. So what is the molarity of a 5-liter solution that was made with 10 moles of KBr, potassium bromide? So molarity equals moles divided by liters. So in this case, we have 10.0 moles in 5.00 liters, so we have a 2.00 molarity solution. Now in the next case, we have 85 grams of magnesium chloride. We have to do moles per liter, not grams per liter. So the first thing we have to do is a conversion here from grams to moles. Now magnesium chloride, MgCl2, so 24.31 grams for magnesium, 35.45 times 2 for chlorine, meaning that we have a molar mass of 95.21 grams. So 85 divided by 95.21 gives us 0.893 moles. Now, to do molarity, we can do 0.893 moles divided by 2.5 liters. 0.893 divided by 2.5 gives us 0.357 molarity. Now, in the next examples, we're going to go the opposite direction. We're going to have molarity, and we want to convert back to moles. So in this case, we have 500 milliliters of a 5 molar solution. To go from molarity to moles, we need to multiply the molarity times the number of liters. Remember, there are 1,000 milliliters in a liter, so this would be 0.5 liters. So in this case, we'll get 2.50 moles of calcium chloride. So molarity times volume will give us moles. If you really want to think through all the various types of equations, moles divided by liters will give us molarity. Molarity times liters will give us moles. And we could even solve for liters. If we want to solve for liters, we would do moles divided by molarity to get liters. So it's just rearranging those variables. The next case, how many grams are required to make 225 milliliters, so 0.275 liters, times 3.0 molarity will give us moles. So we're going to get 0.825 moles of HCl. To go from moles to grams, that's our conversion we learned back in chapter 6. So we need the molar mass, which is 36.46 grams for 1 mole, which is 30.1. We actually only have two significant figures here from the 3.0, so 30 grams of HCl. And I put the decimal place at the end to show the two significant figures. Now we can take this into stoichiometry and use molarity within stoichiometry. Here's a question: how many liters of 0.150 molarity Ki would be required to react completely with 15 grams of lead-2 nitrate? So in this case, we're going to want to go from grams of lead-2 nitrate, PbNO3 2. We're going to have to convert that to moles. Remember, any stoichiometry, the first step, if you are not in moles, is to convert to moles. Then we can go to moles of Ki, and from that we can go to liters of solution. So sometimes this kind of little pathway or road that we're going to follow, steps that we're going to follow, is nice to write out because it helps us to look at what steps we're going to follow in what order. So we're starting with lead-2 nitrate, and we need to go to moles. So 1 mole PbNO3 2. I see a number of you when walking around class the last couple of days doing these problems who are not writing out the full units. If you're not writing out the full units, you're going to end up with a lot of difficulty with keeping track of what you're doing and making sure everything ends up in the right place. So we need to find the molar mass: 14.01 for nitrogen, 16 for oxygen, 207.2 for lead. We got 6 oxygens, 2 nitrogens, and a lead, so we get 331.22. So we have 331.22 grams per mole. Now, from moles, I can go mole to mole. This uses the balanced equation, so 1 mole PbNO3 2, and we're looking for lead iodide, so 2 moles Ki. I'm going to stop at moles here because then I'm going to do a molarity conversion, which is a lot of times you can use the conversion factors, but sometimes easier to see without them. So we end up with 0.09057 moles Ki. Now if we're going to go to liters, liters is going to be equal to moles divided by molarity. Since molarity is moles per liter, rearrange that to be moles divided by molarity to get liters. So the liters here will be 0.09057 moles divided by 0.150 molarity. We get 0.6038 liters. So here we can use stoichiometry as one of our other conversions. The stoichiometry step is this step here. This is a step that we're learning in this chapter. The previous step, grams to moles, we learned in chapter 6. And then this step down here is the molarity step we were just learning in this video. So we really have only the new mole-to-mole conversion, that's the stoichiometry part. The others are just our mole to either molarity, grams, or atoms and molecule conversions. Now, and this is another problem dealing with our stoichiometry with molarity. What I would like to see you do here I'm going to look for this in your notes tomorrow. I would like you to set up your paper with 2 columns. So make 1 column with your attempt and 1 column with my attempt. I would like you to pause the video right now and do your own answer. So in your column where it says mine, put what you think the answer is and all of the work to get to that answer. Then press play again and put my answer in this other column if it is different than your answer, if I do any steps differently. That way you can compare what you're doing versus what I'm doing, and if you have any questions about that, we can answer those at the beginning of class tomorrow. Okay, the first step I would do, now that you've started the video again, is balanced equation. AgNO3 aqueous reacts with sodium chloride, NaCl, aqueous, to form, this is a double replacement precipitation reaction, NaNO3 aqueous and AgCl solid. Luckily in this case it's all balanced 1 to 1 to 1. Our pathway here is going to be to go from molarity of AgNO3 to moles of AgNO3 to moles of AgCl to grams of AgCl. So my first step is to find the moles. So molarity times volume will give me moles. So 1.2 molarity times 0.075 liters gives me 0.090 moles AgNO3. Now for the stoichiometry step, 0.090 moles AgNO3 we're going to go mole to mole, so I want moles AgCl. I want to get rid of moles AgNO3. It's a 1 to 1 ratio. And then I want to go to grams. So for 1 mole AgCl, get the molar mass, 107.87 for silver, plus 35.45 for chlorine. So 143.32 grams. So 0.090 times 143.32 gives me 2 significant figures here, so 12.898, which comes out to 13 grams of AgCl. So bring your notes with you to class tomorrow to be checked off. This will conclude our initial look at stoichiometry. We will quiz on all of this on Friday, and then we will move into limiting reactants and percent yield when we return from the Thanksgiving break.